Our first presentation of the day. This is going to be the copper filtration system. They're sponsored by Encore Water, and I will let it go.
Ladies and gentlemen, welcome to our copper filtration presentation today. We are studying microparticle filtration of copper, sponsored by Encore Water. I am Derek Biggs, team leader.
Fernando Gomez.
I'm Sigmar Horsch.
Jeffrey McKee.
Chandler Smith.
And this is our design day presentation.
Alright, so the problem statement. In Encore Wire's current wire drying process, there are microscopic fines that are contaminating the lubrication system that is used to prevent copper from breaking. These microscopic particles produce heat, friction, and eventually, like I said, produce a manufacturing shutdown because the wire breaks. So our task is to eliminate the current paper filtration that is being used and improve the current filtration amount that they're reaching. So our solution is, number one, this metal mesh screen with a dynamic vibration, as well as a tubular centrifuge. So Encore Wire wants to eliminate the use of paper filtration, and this is important because it decreases filtration costs, and also we can capture part of the copper that would be actually thrown away. This has an environmental impact because it prevents paper from being put into landfills, and is also recapturing the copper to be recycled and made into copper wire. So this overall will impact Encore Wire's manufacturing, purchasing, and discarding. Specific goals the team has set is to achieve the 10.8% copper contamination that they're actually filtering with their current method, replace the paper with a reusable metal mesh screen, build a working proof of concept. As you can see here, we have that. Reduce the amount of human interaction, extend the life of the dip, and maintain safe operation capabilities for their employers.
So some of our design features and testing apparatus, we wanted to produce a repeatable and functional experimental process. So some of the pieces of it. Here we have our 1 horsepower centrifugal circulation pump. It draws here, so here's your inlet pipe from the dirty reservoir, here's your outlet, and here you have a T to split that flow. The reason for this, there's two reasons for this. One of them, a majority of the flow is circulated in this recycle line back into the dirty reservoir, and that'll actually stir up the copper filtrate, the copper fines, so they don't settle at the bottom, so we want to keep those agitated. And then second, this blue handled gate valve allows us to closely regulate the flow that we send through the rest of the system, because we can't flow 100% of it through our module. So from here it goes into the module, goes through the vibration, comes out. So here's the clean that comes out here. It comes around, and then it is disposed back into the clean side of the reservoir right here. So transparent for demonstration. It was transparent before we put the copper in it. It will never be perfectly transparent again. It's portable for showcase. These latches right here in the corner, those can be unlatched. And you can see it's on wheels, so we can split those up and easily transport them. And then we have an evac system. So under this box, we have a little air compressor that when we're done testing, we can isolate certain legs and hit that air, and we can clean up the system. So our testing procedure, we did a 20-minute run time with each the different sizes of mesh. And that 20 minutes was dependent on the 50% duty cycle of that vibration. And Derek will kind of go into that a little later. System was initially filled with 28 gallons of clean water with 24 fluid ounces of copper contaminant in the dirty reservoir. And that was to mimic the copper concentration by weight that Encore is currently working with when we took samples there. So the samples of contaminated water were gathered from the dirty reservoir before each test to regulate and get data of that sample. And then after each run, the samples were gathered from the clean side, and then we were able to make that comparison. So our experimental repeatability, consistent control of operating parameters with a comparable baseline to current paper filtration medium. And then the team tested metal mesh screens of size 115, 95, 75, 60, 25, and then 5 microns.
Data collection. For data gathering, we use a portable nephelometer, which allows us to check the turbidity of the liquid, pretty much just to check how clear the water it was. It just checks the particle concentration on the liquid. It gives about this nephelometer right here, it gives us readings from 1 NTU to 2000 NTU, which NTU stands for nephelometric turbidity unit, which is the unit that turbidity is measured in. And we also use the ICP-OES, which, pardon my accent, let's see, inductively coupled plasma optical emissions spectroscopy, there we go. And with that, we were able to measure the weight percentage of the copper concentrate.
So this is our filtration module 1. It's a self-cleaning filtration metal mesh filter. The principle is to actually have a metal mesh screen instead of the paper filtration in order to prolong use of it and be able to clean it and extend the life and reusability of the system. Some design features of how we designed and built this tank is that we built it out of a polycarbonate material, so where you could view and easily see where caking was occurring, where anything would happen during the process that we needed to monitor or look at and see what we could improve upon. It also has a super quiet electronic vibrational actuator. It has a controlled variable speed and force, so we're able to change the dynamics of the experiment, of the vibrations, with either controlling the force inside the vibrational itself or changing the frequency at which it vibrates, the BPMs. The machined parts of this design are the arms, a vibrator mount, a seal, and the filtering chamber, which houses all the clean lubricant or clean dip that we would have fluid going back over the clean reservoir. The idea is to have basically a seal coupled with a neoprene mesh square, and then our metal mesh. Then we have the neoprene seal again backed up to the housing and backed up to the actual filtration chamber. The filtration chamber, as you can see, if you can clearly see, it goes back here, is sealed, and then goes through there. So when this fills up, it actually looks like it's the dirty water back here, but the clean water is traveling through the piping system.
Looks like that.
So how it works. Basically, our system is to install, it's just basically setting up a mesh screen. Now, you think that's pretty simple, but with adding vibration to it, we're able to enhance the cleaning and prevent caking upon the mesh screen. That's basically what we're trying to do. We're trying to increase the longevity of the screening and the filtering application by inducing vibrational and localizing it in that area. So also what it does is it creates a filtration zone. As you can see on the chart I have where the arrows are rotating back. At this point, particles that are coming up that are not strongly forced to go through the suction of the screen will actually bounce back from the waves of vibration frequency and cake to the gravity slide, which is right here. This slide also incorporates another slide on the back side that goes down and couples into this downward pipe where we believe that the copper should have concentrated. So the mesh screens that we used were a metal mesh screen of 304 stainless steel that were double 12 weave pattern, as you can see on this side. The reason we chose these were not only because of the durability with the vibrational taking apart. We didn't want the mesh screens to break apart and would not work then. So we chose a pattern that would be like that. They were cut into 8-inch by 7.5 inch squares, where a viewable range of fluid that would pass through was 6 inches by 6 inches. The vibrator that we chose to do a 50% duty cycle, which Chandler mentioned earlier, was because the allowed to run, since it's a small vibrator, it's only allowed to run for 30 minutes at a time for 50% of the cycle speed, so at 25 BPMs. If we ran it from 0 to 950, we were able to run it continuously, but the apparatus wouldn't allow for such low vibrations and the frequency of shaking.
So the results for this first module. Like Derek said, we took a sample from the dirty reservoir and we checked the turbidity on that as well. Then we ran the experiment and we took a sample of the clean tank and we checked the turbidity of that. This is the data right here. It is a little bit, the results that we got were not very accurate, but it is important to mention that we did see a lot less concentration of the copper particles on the clean tank. So that was good. And then with the ICP OES, this is the percent copper weight that we got from the results. The red line indicates the current copper filtration that they're using at Encore Wire. So the goal was to beat that. And as you can see with the 25 and the 115 mesh, micrometer mesh, we did beat, or we improved the filtration system.
Originally, our design also used a centrifuge to improve on their current sedimentation system. Encore Wire uses a sedimentation tank where they let the copper particles fall to the bottom under standard gravity, where they then scoop them out. Well, centrifuges would increase the efficiency and the rate at which this occurs. They're widely used in the chemical, oil, and food processing industries for filtering out small particles from fluids. Centrifuges extract particles can extract particles between 0.1 to 500 microns typically. And for our design, we decided to try to build a tubular bowl centrifuge because the centrifuge chamber is fairly simple to build, and we thought it was in the realm of what we were able to do. For our design, as I mentioned, the centrifuge takes place in what is essentially a long pipe. We used a gear ratio to reduce the RPMs of the motor and increase the RPMs of what was being put on the centrifuge. And we incorporated structure to help with the stiffness of the system and rubber washers to improve the damping. A big concern with centrifuges is the vibration analysis to make sure they're steady, and both of these are very important to making sure everything stays stable. We didn't go ahead and build the centrifuge because our team lacks experience, and there's really tight tolerances necessary for these centrifuges to operate safely, and they operate at high energies, so to keep everyone safe, we didn't go ahead and build it. So instead, we used a laboratory centrifuge that Encore has on their premises to run small-scale experiments of the dip under centrifugation. And our procedures for this is we tested a baseline sample of their initial concentration, and then samples at 0, 5, and 10 minutes afterwards. And we tested the samples under standard gravity, and then 1,000 RPMs, 2,500 RPMs, and 4,000 RPMs. And then we sent the samples to the ICP OES in order to measure the concentration by weight of the final samples. And this is the graph of the data of those results. As you can see, they all start at about 1.2% by weight concentration, and then they drop off sharply between 0 minutes and 5 minutes. This tells us that somewhere in there, the concentration drops very rapidly, so you really don't need a whole lot of time, which is good so we can keep the filter system flowing. And then from 5 to 10 minutes, there really isn't much of an increase in separation. There's a little bit, but not a whole lot. So if we were to implement this in a full-scale version, you'd be able to do it quickly and you wouldn't have to worry about running it for long periods of time. Because of the amount of time it took to process each sample, we were only able to take a limited data set. So if we were to run this again, we would definitely concentrate between the 0 and 5 minutes to pin down how long it takes.
So our conclusions, for the self-cleaning filter module, copper particulate concentration is inversely proportional to mesh grain size, which is opposite of what we expected. So common sense would tell you the bigger meshes would allow more copper fines to get through, but from the graph you saw that was not the case. part of the reason we believe that happened, a majority of the particles settled in the system before reaching the filtration stage. So a lot of it, as you can see, settled in the piping. Quite a bit of it settled here on the ramps. So we don't believe that we were able to actually get a true sample at that at the front of the mesh screen. The copper contaminant does not stay suspended in water. So Encore, they actually use a dip solution that is 91% water, 9% of the oil detergent, which obviously the oil gives that fluid a lower viscosity. So the copper fines will stay suspended in there a little better. Whereas we just made the assumption we did water, because we didn't really want to have to transport 40 gallons of that here. I don't even know if we would have been allowed to do that. So obviously with just water and higher viscosity, that copper was more easily settled at the bottom, so we were able to extract as much. For the tubular centrifuge model, we had a 35% improvement between 4,000 and 0 RPM. So the 0, like Sigmar said, is at standard gravity. Sedimentation occurs within 5 minutes under centrifugation. The higher RPM produces better sedimentation, and long centrifugation times have negligible effect past the 5 minutes.
And some recommendations. We believe that if we were to use Encore's current lubrication solution, it will give us a better representation of what this filtration system will do, and therefore will give us better results. A more effective mixing method, like Chandler said, a lot of the copper particles contaminant were settling at the bottom of the tank. They explained how we had a recycling system that will shoot down the water and that will mix it. Unfortunately, that didn't work into our favor too much. It definitely did store the tank, but not as much as we wanted to. So by adding some sort of other mixer that will allow those copper particles to mix in the liquid and then go through the system, that will definitely benefit the project. Before experimentation, run the testing apparatus for a longer run, just so the system can stabilize, and that way the contaminant will go through the entire system.
We wanted to give a special thanks to the Encore Wire Corporation for allowing us to do this project and working with us, especially Justin Rock and Ray Poller. Y'all did a lot for us during this time. It was a great experience, and thank you. We also wanted to thank UNT's Mechanical Engineering Department for giving us the opportunity to do a project like this and finding us the sponsorship. Dr. Qualls, of course, for acting as our professor. And Dr. Fortier for being our faculty advisor during this process and helping us with lots of different unique problems that we were having. And Doug Burns for helping us figure out this pump system over here. We appreciate it. So now we would like to do a live demonstration of the actual filtration process itself. If you like it.
Recycle stage is what happens first. As soon as Derek turns the throttle, the liquid will be able to go and exit into the module 1. We set it at 50% vibration. That's what we tested it with.
As you can see, it's heavy air filling up the tank, and as it fills, a lot of the sedimentation occurs in this process right now because of the solution that we were using. Since it was water, it doesn't stay suspended in the liquid as long as we would like to, where you would experience the actions from the vibrator that we actually thought would be happening. So as the water fills up, you can see the tube line in the back. At the tube line, as soon as the water gets to that point, that's when the filtering actual clean liquid starts coming out and going over into the clean reservoir. This localized bar right here, actually, the stabilized bar in the back of the vibrator actually allows for us to concentrate the vibrations of the vibrator directly onto the screen and its applications. We have a double screen dampening system on both sides. This allows for the cantilever effect of the weight of this vibrator as well as dampening the vibrations to the entire system and shaking not only just the screen but the tank. actually a pretty quiet vibrator. Most of the noise comes from the pump. Do we have any questions? Here.
What's the effect on frequency on the filtering?
So we ran, since we wanted to run a cycle time of around 20 to 25 minutes, and this was predetermined before, we found out in the manufacturing book or manual that came with the vibrator that we could only run it for 30 minutes at 50%. And so we figured a good baseline to start with would be at a 50% vibration frequency. We could run it at between 0 and 950 BPMs for a continuous cycle all the time, but we noticed when we first did the test, we had a very baseline where we didn't run the vibrator at all, and we saw the caking on the screen. We immediately, after 20 minutes of running, we put on the vibrator for 10 minutes to see if it was actually helping, and the 10 minutes helped, and we left it at the 50% duty cycle.
So it's better to run it in short intervals than to just keep it constantly running?
Correct. Well, I mean, if we had a larger industrial size pump, this is, I mean, just for this application, the small, we had to do it in that way. Is there any other questions? Sir?
A couple of questions. First, a technical question. What would be your estimation of the lifetime of the filter they use? And I mean, have you done like a calculation? You could have regular filters, right, like replaceable filters, and then you have the cost of a system like this, right? So, and based on your estimation, and maybe you didn't do this specific calculation, but how long do you think this will last? Because obviously there's some abrasion, right, because of it's a moving, right, part, it vibrates, and would you estimate it lasts for a year, lasts for just a few months, a few years?
I would probably go for like 3-month cycles. The reason I say that is because they don't run the secondary stage filtering process every single day. Or Justin, I mean, do you know if you run it every single day?
Sometimes
Sometimes.
it'll be down.
So yeah, it does have time to actually rest, and I mean, based on what we've seen, the sturdiness and the ability of the screens, I believe that they would actually be able to implement the system. And I mean, the cost of the screens themselves aren't actually that detrimental. You're looking at right there, that screen probably itself cost about $35. So.
And it also depends on a lot of variables, like what kind of flow they'd want to get. If they had multiple ones of these side by sides in parallel, if each one would last longer, they'd probably have bigger surface areas, so less caking. So there's a lot of variables, but yeah, I think the 3 days is.
Well, that is time.
Thank you for your time, and thank you for listening.